Hello, we are from ChemPraxis, and in today's video, we will be covering Physics Paper 3, Variant 1, May June 2021, Question 2. In this experiment, we will be investigating how the rate of cooling of a hot liquid depends on its volume. Let's look at the questions first. We will be provided with a cup, and now we will need to measure D, which is the base of the cup. But before we proceed, let's look at what else is provided for us. So these are the apparatus that are provided for us for the setup. As you can see, we have the cup, stopwatch, 30 cm ruler, thermometer, and the source of hot water. So now we will use the 30 cm ruler to measure the diameter of the bottom of the cup. And remember, when measuring the diameter of anything, we will need to take two measurements of the diameter at different points along the circle. And make sure we are measuring the maximum of 2 points of the circle. So now that we have taken our measurements, we need to take the average of the two diameter measurements that we took to get our accurate D, which is 5.2 cm. Alright, let's proceed on. Now we will need to pour boiling water into the cup until it is approximately 1/3 full, and when the temperature of the water is 75 degrees Celsius, which implies that we will also need to use the thermometer to measure the temperature of the water. Then we will need to start the stopwatch and stop the stopwatch after 2 minutes and take the final temperature, as the heat in the water will dissipate over time. So now we have our stopwatch here with us, and following the instructions given, we will pour the boiling water into the cup until it is approximately 1/3 full, and put the thermometer into the cup and wait for the thermometer to stabilize and drop to 75 degrees Celsius. Keep in mind to not let the thermometer's bulb touch the bottom of the cup, as it will not be accurately showing the temperature of the water. And always hold the thermometer at the top so that we are not blocking any scalings on the thermometer. Also, always read the thermometer by aligning your eyes to level with the top of the liquid column so that there is no parallax error. Now, let's wait for the water temperature to drop to 75 degrees Celsius. Okay, with the thermometer reading reaching the 75 degrees Celsius mark, let's start the timer and wait for 2 minutes. And with the stopwatch reaching the 2 minutes mark, let's take the reading, which is 66 degrees Celsius. So back to our question, we can now record our readings. For our starting temperature, we will have 75.0 degrees Celsius and the final temperature of 66.0 degrees Celsius. As our thermometer can record to the smallest unit of 0.5 degrees Celsius, hence we will need to write our readings to 1 decimal place. Then, we will need to calculate the difference in temperature, which would get us 9.0 degrees Celsius. Now, moving on, we will also need to measure the height of the water in the cup and the diameter of the surface of the water. So let's measure the height of the water first. Make sure to bring the cup up to measure the height, as there is a spacing in between the 0 cm mark to the bottom of the ruler. Then we will measure the diameter of the surface of the water. Since we are only provided with a ruler, we will just try and look from above to estimate what the diameter is. And we'll also need to measure a second diameter at a different point along the circle for us to find the average diameter. With our H and D recorded, let's proceed. Now, we will need to estimate the percentage uncertainty in our value of H. Now, there are two ways of calculating this. We can either use the absolute uncertainty of the ruler, which is 2 to 5 mm over our value of H, or we can take a second reading of H and find the half range between the two values of H over the mean of H2 and H1. Keep in mind, for the half range method, both of your measurements must not be the same, as we cannot have a half range of 0, which would lead us to a percentage uncertainty of 0%, which is invalid. And for the significant figure of your percentage uncertainty, always follow the significant figure of your measured value. In this case, we will round it up to one significant figure. Moving on, we will need to calculate C, where C is this formula right here. Now let's substitute in the values and we will get 92.53 cm squared. And what significant figure should I write it in? Always remember for question 2, it is always the same. For the calculated value, we always follow the smallest number of significant figure of your substituted value. Since both of our values are two significant figures, we can just round it up to 93 cm squared. Moving on, justify the number of significant figures that you have given to your value in C. This also has a very standard answer, so we can just write big D and small d have two significant figures, hence C follows big D and small d as they have the smallest number of significant figures. Moving on to question D, we will need to empty the cup and repeat questions B, C1 and C3 with the cup 2/3 full with water, which I have recorded the data here. Just keep in mind for the temperature difference recorded in the second experiment would be lesser compared to the first, and the height and diameter would be larger compared to the first experiment too. For our C, we will round it up so that we get 100 cm squared. Moving on to question E, it is suggested that the relationship between the difference in temperature, H, and C is by this equation where K is a constant. Now using our data, we will need to calculate two values of K. So we will just rearrange the equation so that we have K as the subject first. Then we can directly substitute the values that we have gotten from our two experiments to get our first and second values of K. For your K values, you will need to round them up to three significant figures and the unit is not a requirement, but you will not be penalized for writing them. Now, it is suggested that the percentage uncertainty in the values of K is 20%. Using that uncertainty, we will need to explain whether our results support the relationship in E. Now, this is a very common question with a very standard way of answering it. We will need to calculate the percentage difference of our K values, then using that percentage difference, we will compare it with the percentage uncertainty given to draw a conclusion. Always remember, if you get a percentage difference larger than the percentage uncertainty given, then your results does not support the relationship. If your percentage difference is smaller than the percentage uncertainty given, then your results support the relationship. So this is the formula to calculate the percentage difference, which you will need to memorize. So after calculations, we get the value of 2.33%, which is smaller than the percentage uncertainty. Now always remember, the actual value of the percentage difference does not matter. The examiners only care about how you calculate and draw the correct conclusions based from your percentage difference. As long as you have a percentage difference larger than 0%, you will be awarded full marks for the question, even if you get a 200% in your calculated percentage difference, as long as you write the correct conclusions. So for the conclusions, we will write as the percentage difference is smaller than the percentage uncertainty, hence results support the relationship in E. If your percentage difference is larger than the percentage uncertainty, you can write as the percentage difference is larger than the percentage uncertainty, hence results does not support the relationship in E. Now for our final question, which is finding four sources of uncertainty or limitations and their corresponding improvements. Always remember that all the uncertainties that you will need to identify are the ones that you will encounter when trying to take measurements. Now you may pause the video to think and write down the possible uncertainties and their improvements. Alright, now for the first uncertainty and its improvements, you can always write this in any of your papers, so you need to memorize this. So you can write, two readings of K are not enough to draw a valid conclusion. And its improvement is, take more readings and plot a graph. Or you can write, take more readings and compare K values. For the second uncertainty, you can write, difficult to measure H, as scale of ruler does not start at the end, or opaque cup used, or water too hot, or ruler in water changes water level. Always identify what is hard to measure first and include a reason. If not, you will not be awarded with marks. And for the improvement, you can write use a transparent cup or ruler without space at the end, or H equals to empty depth minus depth of water. You can always suggest a formula or directly draw a diagram to show how you would get a more accurate measurement if you don't know how to describe them. For the third limitation, you can write difficult to measure D due to parallax error, and its improvement is you can suggest measure D using a vernier caliper, divider, vertical pointers, or a traveling microscope. As our thermometer can only measure up to 0.5 degrees Celsius, which is not precise enough, for the fourth limitation, you can write large percentage uncertainty in difference in temperature, or thermometer not precise enough to measure a small change in temperature. And for the improvement, you can say use a more precise or more sensitive thermometer, or use a thermometer with reading up to 0.1 degrees Celsius, or using a thinner caliper in thermometer, which will increase the sensitivity of the thermometer. To decrease the large percentage uncertainty mentioned, we can say allow the experiment to go on for more than 2 minutes, which will increase the difference in temperature, causing the percentage uncertainty to decrease. There is also an additional uncertainty that we can write, which is difficult in taking temperature at the end of 2 minutes period, as we cannot look at both the stopwatch and the thermometer simultaneously. For the solution, we can write use sound to mark the 2-minute period, or use temperature probe linked with a data logger system, or record a video with thermometer and stopwatch in view and play back frame by frame to get the temperature reading. So this is the end of the question. If you like the video, don't forget to like, share, and hit that subscribe button. This is ChemPraxis, and thanks for watching.